Hello everyone, in this section we'll learn about the contraction mechanism of skeletal muscle. During muscle contraction with shortening of the skeletal muscle fiber, there is no change in the length of either the thick or thin filament, and the shortening is actually due to the swelling motion of many cross bridges that forces the thin filament sliding toward the center of the sarcomere. The thick filaments are composed almost entirely of the contractile protein myosin. Rows of myosin. The myosin molecule is composed of 2 heavy chains and 4 light chains with 2 global heads and a long tail. The tail lies along the axis of the thick filament, and the 2 global heads extend out to the sides, forming the cross bridges. Each global head contains binding sites, one for actin or one for ATP. The ATP binding sites also serve as enzyme, and ATPase that hydrolyzes the bond ATP. The thin filaments contains the contractile protein actin as well as 2 other proteins, troponin and tropomyosin, that play important roles in regulating contraction. Roles of actin, tropomyosin, and troponin. A double-stranded actin protein forms the backbone of the thin filament. The tropomyosin molecules are long units, and in the resting state, they lie between the cross bridge of the myosin and actin. That interaction cannot occur between them to cause contraction. Troponin are global units connected with the tropomyosin and have 3 subunits. Troponin I, it has a strong affinity for actin. Troponin T, it has strong affinity for tropomyosin. Troponin C, it has a strong affinity for calcium. Molecular process of contraction. General molecular process of contraction. In relaxed state of sarcomere, the binding sites on the normal actin filament are actually physically covered by the troponin-tropomyosin complex and cannot attach to the head of the myosin or thick filament to cause contraction. During contraction of sarcomere, calcium ion combine with troponin. C. Conformational change of troponin-tropomyosin complex, uncovering the binding site of actin. The binding site of actin attached to the head of myosin of the thick filament to cause contraction. Molecular movements during contraction. Power stroke theory of contraction. Power stroke, when the heads of the myosin attached to the active site of the actin, the profound changes is in the intramolecular force between the head and the arm of the cross bridge occur to cause the head tilt towards the arm and drag the actin filament along with it. This tilt of the head is called power stroke. After tilting, the head immediately breaks away from the attachment site and returns to its normal perpendicular direction. In this position, it can combine with a new active site further along the actin filament to cause a new power stroke, and the actin filament move another step again and again, and the actin filament can walk along in the myosin to shortening sarcomere. Cross bridge circle. The circle can be summarized briefly in 4 steps as follows. Attaching the myosin cross bridge to the actin filament. Movement of the cross bridge producing tension or moment in the thick filament. Detached of the cross bridge from the thick filament. And analyzing the cross bridge so that it can again attach to a thick filament and repeat the circle. Excitation, contraction, coupling. In a resting muscle fiber, the concentration of the calcium in the cytosol is very low. Very few of the calcium binding sites on troponin are occupied. Thus, cross-bridge activity is blocked by tropomyosin. Following action potential, there is a rapid increase in cytosolic calcium concentration and calcium binding to troponin, removing the block effects of tropomyosin and allow cross-bridge circling. The source of the increased cytosolic calcium is the sarcoplasmic reticulum within the muscle fiber. The T-tubular are in initiate contact with the terminal cisternae of the sarcoplasmic reticulum. During a T-tubular acting potential, the activation of the special protein in the T-tubular membrane induced a conformation change in another protein. Retinoidin receptor, which forms a calcium channel. Calcium is thus released from the terminal cisternae of the sarcoplasmic reticulum into the cytosol, activating cross-bridge cycling. Once the calcium ions have been released from the sarcoplasmic tubule and have diffused among the myofibrils, muscle contraction continues as long as calcium ions remain in high concentration in the sarcoplasm. However, a continually active calcium pump located in the walls of the sarcoplasmic reticulum pumps calcium ions away from sarcoplasm back into the sarcoplasmic tubules. This pump can concentrate calcium ions about 10,000-fold inside the sarcoplasmic reticulum. The massive transfer of calcium into sarcoplasmic reticulum causes virtual total depletion of calcium ion in the sarcoplasm, and the muscle remains relaxed. That's all for today. Thank you.